Today we're going to go ahead and work on 4.2, the structure of a nuclear atom. So as we go through this, again, you can go through the lecture slides all by yourself, or you can go ahead and stick on here with me. So let's look at the first question here is how do scientists determine structures that are inside an atom? So how do we know what's inside the atom? We can't see it. Well, doctors look at x-rays and they see the bones and they can see whether or not the bone is cracked or something like that, so they can see through the skin. An atom's almost the same way. Okay, so what are our key things that we're going to go over? Subatomic particles. So there are three kinds of subatomic particles that we're going to talk about. We'll talk about what they are, and we're going to talk about that much of Dalton's atomic theory that we talked about yesterday is actually accepted today. There is one important change, however. It's that atoms are known now to be divisible. Okay, before Dalton said that they're indivisible like Democritus, but they are divisible. We can break them down. Typically, we have to use a particle accelerator or something like that to put them into to break them down. So they can be broken down into even smaller, more fundamental particles that we call subatomic particles, and that's really what we're going to talk about today. There are three kinds of subatomic particles: electrons, protons, and neutrons. We need to know what they are, approximate size, and if they have a charge or not. Okay, so we start off with electrons. J.J. Thompson, he discovered the electron, and that electrons are, let's go back to that. Let's go back one. That electrons are negatively charged subatomic particles. But how did he find that out? Okay, let's go ahead and watch this short video.
My job is to make college easier because students have a lot on their hands.
In this video, we're going to talk about how J.J. Thompson discovered the electron in 1897 using the Cathode Ray Tube experiment. So these days, we think about atoms kind of like this. They're made up of a variety of smaller subatomic particles. But in the late 1800s, it was all about John Dalton's model of the atom. In the early 1800s, John Dalton had proposed that all matter, all stuff, was made up of tiny, indivisible particles called atoms. At first, not many people believed him. But throughout the course of the 1800s, more and more scientists got on board with this idea. But it remained an open question whether the atoms were really indivisible. Were they like tiny little billiard balls, hard and solid? Or were they made of smaller things? No one really knew the answer to that. But J.J. Thompson was able to answer part of that question when he discovered the electron. He discovered that it was much smaller than atoms. He discovered that atoms had electrons. And so he was able to say for the first time that atoms weren't totally solid and indivisible, but they were made up of smaller, subatomic particles. Let's look at how he discovered the electron. So Thompson used what's called a cathode ray tube. It's a big tube of glass that's kind of like a bottle. You can imagine it's sort of like this soda bottle. It's sealed all over, and then you pump all the air out of it. Okay, and it has these two pieces of metal at this end. So Thompson connected these two pieces of metal to a power source, and here's what happened. A ray shot from this piece of metal across the tube and created a glowing spot over here when it hit a special coating on the inside of the glass. Now, Thompson didn't know what was going on, but what really was going on is that electrons from this piece of metal were shooting out. They were attracted to this piece of metal, which has an opposite charge, but they were moving so fast that they shot all the way across the length of the tube. Anyway, Thompson sees this ray, and he gets curious as to what it's made of. And so he asks the question, the stuff that the cathode ray is made of, does it have an electrical charge? And here's how he attempts to answer that question. He takes two metal plates and puts them on either side of the cathode ray tube. And then he turns on electricity, which makes the top plate positively charged and the bottom plate negatively charged. And check out what happens to the cathode ray. When he turns on the power, he sees that now instead of going straight through, the cathode ray bends up. It bends up towards the positively charged plate. So based on this, he reasons that the cathode ray must be made of stuff that's negatively charged, since it's attracted to the positively charged piece of metal, and he knows that opposite charges attract. But just because he wants to be very careful, he's a very careful guy, he tries to check this another way. So he uses a magnet. If something has an electrical charge and it's moving, a magnet will push it in particular directions. So he takes a cathode ray tube, if you want to think that this marker is kind of a cathode ray tube, and he surrounds it with a magnet, just like this. We can kind of show what goes on by slipping the magnet under like this. So anyway, he puts the magnet here, and he sees now that the cathode ray bends in the other direction. It now moves downward. Now, if the cathode ray is indeed negatively charged, this is exactly how you would expect it to move in the presence of a magnet like this. So this is just further confirmation that whatever makes up the cathode ray probably is negatively charged. So he takes the data that he gets from these experiments, and he's able to draw a few important conclusions about cathode rays and what makes up atoms. Okay, so based on the outcomes of the experiments with the charged plates and the magnet, Thompson is able to conclude that cathode rays must be made of stuff that is negatively charged. Okay. He combines the information that he got from the experiments that I just told you about with some other data that he collected. And he's able to come to the conclusion that the particles that make up cathode rays are 1,000 times smaller than a hydrogen atom. Hydrogen atoms are the smallest atoms. So this thing that's in the cathode rays must be really, really tiny compared to an atom. And finally, Thompson swaps out the type of metal that's in the cathode tube. He uses a variety of different types of metal, but he finds that all of the different metals he uses give off the same cathode rays, and regardless of what metal he uses, the size of the things that are in the cathode rays is exactly the same. So based on these three conclusions, he's able to come up with the idea that atoms have tiny, negatively charged particles inside them, and these things that we're talking about here are electrons. Now, if you're like me when I first learned this, you might be confused how these conclusions definitely tell him that there are electrons inside atoms. I remember when I first learned this stuff, I was thinking like, wait, doesn't this just show that electricity or cathode rays have negatively charged stuff? How does this tell us anything about the atoms? Okay, here's why. At the time that Thompson does his experiment, everyone, for the most part, agrees that all things are made up of atoms, that atoms are the smallest things that make everything up. They're like the smallest things in the universe. So if Thompson is able to show that there are even tinier things, well, where are those tiny things coming from? They have to be coming from atoms because everything's made of atoms, right? That's the only place they can be coming from. And even if electricity, even if you want to say, oh, well, he's just showing that electricity is made of electrons, well, then still, where are the electrons coming from that make the electricity? The electrons have to be coming from other atoms. And since he can remove these pieces of metal and swap other metals in, and he still gets electrons. It again shows that all different types of atoms are able to release or give off electrons. So they must be in there to begin with. Anyway, these conclusions that Thompson comes to have dramatic effects on how scientists think about what the atom actually looks like. Now, at the beginning of the video, we said that in Dalton's atomic model, atoms are indivisible, that they're not made of anything smaller. But when Thompson discovered that atoms have tiny negatively charged electrons inside them, he essentially disproved this model, at least the part about the indivisible atoms. So here is the model of the atom that Thompson comes up with. He realizes, first of all, that electrons are negative. We already talked about that. But then he notices that on the whole, atoms in general are usually electrically neutral. So even though they have these negatively charged electrons inside them, the atoms as a whole don't have charge. So Thompson realizes that in order for the atoms not to have a charge, there must be some positive charge in the atom that can balance out the negative charge of the electrons. And then the positive and the negative balance out, and the atom then as a whole doesn't have a charge. So he comes up with a model that he calls the plum pudding atom. Now, plum pudding is kind of a British thing, so if you're American, it might be better for you to think about this as like the blueberry muffin model. And here's how it works. Thompson imagines that the atom is like a blueberry muffin, and that electrons are stuck in this atom the way blueberries are stuck in a blueberry muffin. So you have these little electrons that are stuck in the atom, but then they're surrounded sort of by a dough. And the dough, like in a blueberry muffin, keeps these electrons or blueberries held in place, but the dough itself has a positive charge. And it's that positively charged dough that is what balances out the negative charge of the electrons. And so together, they don't have any total net charge. So the atom is electrically neutral. So that's how J.J. Thomson's discovery of the electrons leads to this plum pudding model. But now J.J. Thomson didn't have it quite right, because it turns out that the positive charge in the atom isn't sort of spread out in this dough or pudding, but instead it's concentrated right in the center of the atom, where the nucleus is. So that's going to be the next step in discovering what the atom really looks like. If you're interested in how scientists disprove J.J. Thomson's plum pudding model, check out Rutherford's gold foil experiment, where he discovers that atoms have a very small, very dense, positively charged nucleus.
So now we're going to go ahead and move on to what J.J. Thomson did. So he performed experiments, as the gentleman just told you about. He sealed gases in a tube. He filled both in. He had metal discs and electrodes, and he connected an electricity source. It was kind of like this that he was doing. And one of the things that told us was, and we call it a cathode ray tube, and that electrons traveled across it, okay, as he said. But when he put a magnet near it, and again, this is the same thing. Here's their little shooting of beam of electrons, and we noticed that it was pulling it towards it. So when I look at this, it's pulling it towards us. These are negative. This must be the positive plate. So the positive plate attracts that, and knows that the other one would repel it. And he did the same thing with a magnet. Now, at first, Thompson called these electrons corpuscles, but later they became named as electrons. Okay, here's a demonstration picture of just such a experiment being done. Okay, so to test his hypothesis, Thompson set up the experiment to measure the ratio of the electron's charge. Well, he found that the ratio was constant, so It was constant throughout everything that he did. It didn't matter what element he was talking about, the ratio for the electrons was always constant. So the charge to mass ratio of the electron didn't depend on the type of gas or any metal that was used. It was always constant. So he concluded that electrons are a component of all atoms of all elements. Okay. Now, Millikan did something called the oil drop experiment, which actually helped us out with something, and he found out that the actual charge of that subatomic particle. We don't really know that the charge is, we just know that that charge is equal but opposite that of a proton. Okay. So Millikan found out and calculated the electron's mass from that charge. And we knew that the mass was extremely small to begin with, but we really know that it's 1/184,000th that of the hydrogen atom, which the hydrogen atom is only really made up of a proton, okay, no neutron. So again, it's that much smaller. So if we really round it up, we say that a proton, which is in the atom, hydrogen atom, is almost 2,000 times larger than the electron. So electron's 2,000 times smaller than a proton. So it doesn't matter how many electrons are there, they don't add up as far as weight goes. Okay, protons and neutrons. So we think, when you think through the problem of using 4 simple ideas about matter and electrical charges, okay, atoms have no net electric charge. They're electrically neutral. Electric charges are carried by particles of matter. Electric charges always exist in whole number ratios, which means we can't have a half a charge. Okay. And when a given number of negatively charged particles combines with an equal number of positively charged particles, it ends up being electrically neutral. And that's what everything wants to get, is electrically neutral. So it follows that a particle with 1 unit of positive charge should remain when a typical hydrogen atom loses an electron. So if a hydrogen atom, since it's number 1 and only has 1 proton and 1 electron, it loses the electron and it becomes positively charged. Okay. Mr. Goldstein observed the Cathode Ray Tube that J.J. Thompson did, and he found that rays are traveling the direction opposite to that of the cathode rays. Okay. And he called these particles protons. So he kind of observed and went one step on top of J.J. Thompson. But all we know is that Goldstein is the one that discovered these, and they called them protons. Okay, neutrons were discovered by James Chadwick. They're subatomic particles with no charge, but they do have a mass equal to that of a proton. So again, they're 2,000 times larger than the electron. Now the mass is important because what the mass does is allows the nucleus to stay together. Okay. So here's kind of the table of what it is. We see that the electrons are extremely small. It's a lot smaller than these protons and neutrons. We see the charge, the relative charge of the electron is equal but opposite that of the proton, with the neutron being neutral. Okay, so although protons and neutrons are extremely small, theoretical physicists believe that they are composed yet of smaller subatomic particles called quarks. We're not going to talk about quarks in this class, just the subatomic particles, not the smaller subnuclear particles. Okay, so what evidence did J.J. Thompson have that led him to conclude the cathode ray was a stream of tiny negatively charged particles? Well, the ray itself was attracted to a metal plate with a positive electric charge. And Thompson knew that opposite charges attract and like charges repel. So because it was attracted to that positive plate, that those particles must be negatively charged. Okay, the nucleus, the atomic nucleus. How can we describe the structure of the nuclear atom? Now again, J.J. Thompson did the plum pudding model, or we could say the blueberry muffin model, where the electrical charges are just throughout the atom itself. But that's not really what happened. They wondered where the atoms were, how the particles were put together. Okay, so we know that J.J. Thompson used that plum pudding model, and it was good for a while, but it didn't explain everything. Okay, now again, when he said it, it was like lumps of positive charge, like raisins stuck in a dough and bread. Okay, now it wasn't until Ernest Rutherford, okay, who was born in New Zealand, came along. And what did he do? Now, Rutherford did what's called the gold foil experiment. Now, the gold foil experiment basically shot alpha particles through gold foil. And by shooting them through gold foil, he realized that it almost always went through, it never bounced out. So if the whole atom was made up of something really hard, that it would bounce off. But that's not what Rutherford came up with. Let's see what he did.
My job is to make college easier because students have a lot on their hands.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists, because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil. See what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thompson had suggested, kind of an amorphous blob, then you expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom is.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
Okay, so that was the gold foil experiment. So one out of every 8,000 bounced back. Okay, so a lot of them went through. 8,000 of them went through, but every once in a while one would bounce back. That meant that it wasn't that kind of amorphous blob that they said where everything would just kind of go through, but every once in a while it would hit something. That means that there was something hard, but it was extremely small, and they found that in the center. So almost everything passed through, but every once in a while one bounced back. Kind of like this, where everything would go through. Sometimes it was altered just a little bit because it would get close to the nucleus, and sometimes it would bounce back. Okay, so again, 1 out of every 8,000 bounced straight back towards the source, okay, of where those alpha particles, which is that radioactive material that we've been talking about. So how do scientists see inside an atom to determine the structures that are inside the atom? Well, they use other different things and how the particles react, like negatively charged electrons or positively charged alpha particles, going through it and seeing what they do. That's just an experiment that science does. So Alfred Rutherford, okay, did the atomic model, and he proposed that the atom was mostly empty space. And I can give you another kind of explanation of it. It's mostly empty space. If you think of Ford Field, where the Detroit Lions play football, if we end up having a nucleus that was the size of a marble and put it on the 50-yard line, the electrons would be zooming around outside the stadium, extremely small, and all the stuff in between, nothing there. But we don't know exactly where the electrons are too. So all of the mass and most of the mass are concentrated in that small region. Now again, it's the positive charge. We also find out later that the neutrons are in there too. And the neutrons, even though all these positively charged protons are there, what keeps them there is the nuclear force of having the neutrons creating mass and executing a little bit of gravity inside that nucleus. Okay, so Rutherford's model, known as the nuclear atom, that the protons and neutrons are located in the positively charged nucleus. The electrons are distributed around the nucleus that occupy most of the volume, but we don't know exactly where they're at. We can't see where they're at, and that's where you see just kind of an electron cloud. So according to Rutherford's model, the nucleus is tiny, densely packed compared to the whole atom. Okay, and I already said that with the other one. So Rutherford's model turned out to be incomplete. Okay, his model had to be revised in order to explain the chemical properties of elements. And we'll talk about that later. So what evidence did Rutherford's gold foil experiment disprove J.J. Thompson's plum pudding? It was really that some of the particles bounced back. They were deflected at small angles or even bounced back. And that's why there wasn't nothing, or with J.J. Thompson, where it said he thought everything should go right through. Almost everything did. Remember, it was only 1 in every 8,000 that bounced back. Well, that's the end of the lesson notes. Hopefully helped you out. And again, you'll be able to also look at these notes too without having them narrated by me. Hey, as always, go Mohawks. Nelson out.